What if our sun was a giant? What if Earth had formed around a star so massive and bright that noon looks like standing inside a welding arc and the star fills half the sky? There are few stranger ways to rethink our place in the universe than to change the very star that defines our days. We are used to a small, polite yellow sun. It warms us, it sets and rises with reassuring regularity. But imagine looking up from an Earth-like planet tens of times farther out than we are now, and still feeling blistering daylight. Above you hangs a blue-white giant star, so swollen it stretches from horizon to horizon. Shadows are razor sharp. The sky glows with a harsh, icy brilliance. You are at a comfortable temperature. Your oceans have not boiled, yet the light feels wrong. This is an Earth in the Goldilocks zone of a giant. The numbers are extreme. A star 10 times the mass of our sun can shine thousands of times brighter. This means its habitable zone is pushed tens of astronomical units away, out where our Kuiper belt lives. From the ground, your sun is not a neat coin in the sky. It is a blinding disk so large that sunsets take hours, and true night barely exists. But while the temperature might be familiar, the radiation is not. The air above this world is constantly hammered by brutal ultraviolet light and high-energy particles. Auroras rage across every latitude. Any atmosphere is fighting for its life, stripped from the top down by a stellar wind, more like a sandblaster than a breeze. Could biology adapt to that, or would the first fragile molecules of life be destroyed faster than they form? In the hunt for alien life, we usually focus on calm, steady stars. We know that Earth-like planets can be habitable around them because we are the proof. So it should be noted that our entire history, our biology, even our sense of time itself, is tuned to a star that burns slowly and lives for billions of years. If we had been born under a giant, racing through its fuel in a few million years, would complex life ever have a chance? Or did we simply get lucky with a quiet yellow sun that offers the bare minimum stability for life to emerge? So it's time to find out the truth. Would an Earth around a giant star be a kind of cosmic paradise with a wide, generous habitable zone and endless, brilliant daylight? Or is it a short-lived blast furnace where planets are stripped, atmospheres shredded, and any hope of oceans and continents erased before they can settle? Astronomers are starting to test this, using new data from telescopes including JWST to search for planets around massive stars. Early results hint that our sun may sit in a surprisingly narrow sweet spot. Optimistically speaking, giant star Earths might exist, but if they do, their time may be running out almost as soon as they begin. So, let's begin. Why the star you orbit decides your fate. If we really want to know what an Earth around a giant star would be like, we have to start with something simple. What decides a planet's fate more than anything else in the universe? It is not the continent layout, or even the atmosphere at first. It is the star. Its mass, and the light that mass produces, quietly set the rules for everything that follows. This means where planets can form, how long oceans can last on the surface, and even whether fragile molecules like Dina can survive the radiation pouring down from above, are all written in the language of stellar mass and luminosity. On the main sequence, there is a surprisingly sharp rule. Luminosity scales roughly as mass to the third or even the fourth power, so if we took a star 10 times the mass of the sun, it could shine up to about 10,000 times brighter. The familiar Goldilocks zone would not sit at 1 astronomical unit anymore. It would be pushed tens of AU outward, far beyond the orbit of Saturn in our own system. An Earth-like planet in that zone would orbit slowly, under a sky dominated by a blazing blue-white sun. But while more massive stars create huge, bright, habitable zones, they pay for that brilliance. They burn through their nuclear fuel at breakneck speed. A 10 solar mass star might only live 20 million years or so. Compare that with the sun's comfortable 10 billion year main sequence lifetime. In the hunt for alien life, that difference is brutal. Life on Earth took hundreds of millions of years just to become complex. So, can chemistry, oceans, and evolution really race the clock around a giant star and win? At the other extreme, small stars, especially red dwarf stars, flip the trade-off. They are dim, their Goldilocks zones are tiny and pressed in close, and planets there risk tidal locking and intense flares. Yet those same stars can burn for trillions of years. It should be noted that this sets up a cosmic dilemma, a short, bright window around massive stars, or a cramped but almost eternal window around cool, dim ones. Our sun sits uneasily between these two lifestyles. Adding to the puzzle, massive stars are rare, distant, and violent. Their intense ultraviolet light, fierce winds, and frequent outbursts strip their protoplanetary disks quickly, perhaps in just a few million years. That makes planets hard to grow. and even harder to detect. Even with JWST, our data on giant star worlds is still blurry, so it's time to find out the truth. If we can understand how disks and planets behave around these behemoths, we might finally see whether the sun is a narrow sweet spot between dim longevity and deadly brilliance, or whether giant star Earths could truly compete. And what we discover next may force us to rewrite what habitable really means. Meet the giants, blue behemoths, and their brutal physics. To understand what Earth would face, we first need to meet the giants themselves. What exactly do we mean by a giant star here? We are not talking about swollen red giants at the end of their lives, like a future version of our sun. Instead, we mean the heavyweights of the main sequence, hot blue O and B type stars, roughly 8 to 20 times the sun's mass, still in their prime hydrogen-burning phase. These are the stars that turn star-forming regions into glowing cosmic sculptures. Visually, they are nothing like our yellow sun. Their light is blue-white, almost harsh, with surface temperatures of 15 to 30,000 Kelvin or more. This means each square meter of their surface radiates an enormous amount of energy, because luminosity climbs steeply with mass. A 10 solar mass star can shine 10,000 times brighter than the sun. The result is a Goldilocks zone, pushed far outward, tens of times farther than Earth's orbit, lit by what would look, from a planet, like a welding arc in the sky. But brightness is only half the story. These stars blast their surroundings with powerful stellar winds and intense ultraviolet radiation. Their winds can strip gas from nearby disks, their UV light can tear molecules apart and ionize entire clouds. In the hunt for alien life, these are not the gentle, stable beacons we usually hope for. It should be noted that such stars are rare. Most stars in the Milky Way are small, quiet red dwarf stars. Massive O and B stars are the opposite, intrinsically scarce and incredibly short-lived. A 10 solar mass star may live only around 20 million years before dying in a supernova. So where do we find them? Typically in crowded young star-forming regions like the Orion Nebula, where their radiation carves pillars and cavities in the gas, shaping the entire system around them. So what does that environment mean for planets? For a long time, astronomers assumed it was almost hopeless for small, rocky worlds. Intense UV and X-rays would erode atmospheres, strong winds would sandblast protoplanetary disks, rapid evolution would slam the habitable window shut before complex life could even begin. And in these dense clusters, close stellar encounters could yank planets out of stable orbits altogether. But while theory painted a grim picture, new data are complicating that story. With JWST and other observatories, we are starting to see dusty disks and even candidate planets around massive stars. Optimistically speaking, nature may be more efficient at building worlds in these extreme environments than we expected. So, let's begin to imagine. If an Earth-like planet formed there, its entire history, from the first raindrop to the final extinction, would unfold in a cosmic blink. This means that to judge whether such an Earth could ever be habitable, we have to compress everything we know about planetary birth, climate, and death into a few frantic million years, and ask how long a fragile atmosphere can survive under a blue star's relentless glare. Our new eyes on harsh suns, JWST, and the massive star frontier. So, if everything has to happen in fast forward around a giant blue star, how do we actually check whether nature can keep up? We cannot rewind our own solar system, but we can look outward at other stellar nurseries and watch the verdict being written in real time. This is where the James Webb Space Telescope steps in as our cosmic judge. Webb is not just another space telescope, it is a cold, infrared-optimized eye, parked 1.5 million kilometers away at the L2 point, shielded from the sun and Earth, so its mirrors can cool down and see the faintest glow of warm dust. Its spectrographs can pick out the fingerprints of molecules in a thin atmosphere, or the heat from a protoplanetary disk only a few hundred degrees above absolute zero, light-years away. But while JWST is the new star witness, it should be noted that it does not work alone. Hubble gave us sharp optical images of glowing gas. Spitzer revealed dusty disks in the infrared. ALMA, the giant radio array in Chile, mapped the cold gas and dust where planets are born. Together, these instruments have turned places like the Orion Nebula and its trapezium cluster into laboratories where massive O and B-type stars sit right next to fragile planet-forming disks. So, let's begin with what they actually show. In the hunt for alien life, we often focus on quiet red dwarf systems, or sun-like stars with calm Goldilocks zones. Here, we look at the opposite, giant stars, blasting their surroundings with ultraviolet light. In Orion, Hubble first revealed proplyds, teardrop-shaped disks, literally being photo-evaporated by nearby massive stars. ALMA measures how much gas is left. Webb can now see deeper inside, tracing the warm dust structure and the remaining gas content. This means JWST has become a kind of verdict machine. By measuring how dense those disks are, how quickly their gas disappears, and how their inner regions are carved out, we can estimate disk lifetimes near massive stars. Around the most extreme O-type stars, the data suggest that disks can be stripped away in under 1 to 3 million years. That is barely enough time to grow rocky embryos, let alone full Earth-like planets with oceans and a protective atmosphere. Pattern interrupt. What about stars that are only slightly less monstrous? Around B-type stars, the story softens a little. Disks survive longer, a few million years more, and JWST is beginning to see more complex structures, gaps, rings, hints that planets are trying to form before the clock runs out. Optimistically speaking, there might be a narrow window where rocky worlds can assemble, so it's time to find out the truth. If Earth had tried to form in one of these harsh, blue-lit nurseries that JWST is dissecting, would it have had time to grow beyond a dusty embryo before its whole birth cloud was blown away? And if it somehow did, what kind of world would that rushed, radiation-battered Earth actually become? Paradise or blast furnace? The giant star Earth dilemma. So if a rocky world does somehow emerge from that chaos, what happens next? Does it become the ultimate upgrade pack for Earth, or a beautifully lit death sentence? Let's frame it as a brutal either, or take an Earth-like planet and drop it into the Goldilocks zone of a giant star. Not a gentle yellow sun like ours, but a blue-white beacon, tens of thousands of times brighter. Does that world turn into a wide, sun-drenched paradise, with oceans spread across an enormous orbit? Or does the same light that keeps it warm strip its atmosphere and sterilize the surface before life has a chance to take hold? On the Paradise side, the picture is seductive. A 10 solar mass star can shine roughly 10,000 times brighter than the sun. This means its habitable zone is pushed way out, tens of astronomical units from the star. Our Earth-like planet could cruise on a long, stately orbit with years that last decades and far less risk of tidal locking. Day and night would both be stable. The sky would hold a brilliant, blue-white sun that never flares like a temperamental red dwarf, and the planet would have huge orbital real estate where multiple worlds could all be comfortably temperate. But while the orbit looks peaceful, the radiation does not. That same star floods its system with intense ultraviolet light and fierce stellar winds. High-energy photons slam into the upper atmosphere, heating it, puffing it up, and driving it away into space. The habitable zone may be far out, but the blast furnace effect is still there, just stretched over a larger scale. Instead of a quiet cradle for oceans and continents, we might be looking at a world whose air is peeled off in a few 100 million years, leaving rock and ice under a hard, bright sky. And there is another problem. Massive stars live fast and die young. A 10 solar mass star may only last 20 million years on the main sequence. In the hunt for alien life, that is the blink of an eye. Complex life on Earth needed billions of years. Even the jump from simple cells to animals took longer than the entire lifetime of a blue giant. So it's time to find out the truth. Is our sun close to the bare minimum for slow, layered, complex evolution, or could a civilization somehow arise in the fast lane, building telescopes and cities in the brief moment before its star races toward supernova? It should be noted that the answer may not be a simple no. Optimistically speaking, there might be a narrow, almost absurdly fine-tuned path where life sprints instead of strolls. A planet with just the right mass, just the right atmosphere, forming just far enough out to endure the radiation while evolving at breakneck speed under a ticking stellar clock. In the next sections, we will use star physics, disk evolution, and real exoplanet data to ask whether that path is real or pure fantasy. Welcome to the Fast Lane, how we'll dissect giant star Earth. So, let's begin our tour of this extreme world properly. And this is where we take real astrophysics and use it to stress test the limits of what a habitable planet can be. In the hunt for alien life, we usually look for calm, Earth-like worlds in the Goldilocks zone of quiet stars. But while that approach is sensible, it leaves out a brutal question. What happens if we drop an Earth into the blast furnace of a giant star and ask, with no safety net, whether life could ever stand a chance? This is not just a sci-fi backdrop. This means we are going to use giant star Earth as a laboratory, a way to push our equations, our simulations, and our intuition about habitability right up to their breaking point. If our theories survive here, they are probably solid. So, what is the roadmap? First, we will scale up from our sun to truly massive stars, the blue giants and their slightly smaller cousins. A star 10 times the sun's mass can shine thousands of times brighter, so the habitable zone is not a cozy inner orbit. It is flung tens of astronomical units away. We will map out where an Earth-like planet would have to orbit just to receive the same energy we get here, and ask what that does to seasons, day length, and the basic rhythm of climate. Second, we will step back in time to the protoplanetary disk. Around a giant star, the disk is blasted by intense ultraviolet light and powerful stellar winds. It should be noted that these disks can disperse in only a couple of million years. We will look at how that shifts the snowline, how fast dust and ice can grow into planets, and whether an Earth-mass world at the right distance is even likely to assemble before the raw materials are stripped away. Third, we will dive down to the surface. What does the sky look like when your star is so bright it turns noon into a welding arc? How does the atmosphere respond when high-energy photons are constantly trying to tear it off into space? We will explore radiation levels, magnetic shields, atmospheric escape, and how fast climates could swing on a world racing against its own star's aging. Finally, we will follow the star itself as it burns out, swells, and dies. Optimistically speaking, could complex life emerge before the supernova, or does the window slam shut long before evolution can catch up? The goal behind all of this is simple: to understand why planets around massive stars are so rare, so fragile, and so short-lived, and what that quietly says about how lucky we are to orbit a very average star in a very ordinary system. Along the way, we will move back and forth between billion-year stellar lifetimes and very human imagery: how often the sky would change color, how quickly coastlines might freeze or boil, how it would feel to watch your star brighten measurably within a single lifetime. Each section will solve one piece of the puzzle: where to orbit, how to form, how to survive, while raising a sharper question for the next one. So it's time to find out the truth. When we finally arrive at the supernova, will giant star Earth have ever been truly habitable, or will we realize the real horror much earlier, in a place we do not expect? Scaling up the sun, mass, luminosity, and the shifting habitable zone, if our sun controlled everything about habitability, this story would already be over. But what really happens when we scale the star up? How does that change where an Earth-like planet must live, and for how long? So, let's begin with the most important rule of giant stars, the mass-luminosity relationship. As we increase a star's mass, its brightness does not rise gently, it explodes upward. Roughly speaking, luminosity scales as mass to the third or even fourth power. This means that a star 10 times the sun's mass is not 10 times brighter. It can shine around 10,000 times more intensely than our calm yellow sun, in the hunt for alien life. That single fact completely reshapes the Goldilocks zone. A planet that wants Earth-like temperatures has to move far away just to avoid being incinerated, because the energy you receive drops with the square of distance. A star that is 10,000 times more luminous needs its habitable orbit to be about 100 times farther out. Instead of 1 astronomical unit, we are talking tens of AU. Let's turn that into a concrete picture. Imagine a giant star radiating roughly 20,000 times the sun's luminosity. An Earth-like world receiving the same total energy as we do would orbit at almost 30 AU beyond Neptune in our own system. Inside that orbit, for tens of AU, space would be flooded with harsh light yet still physically cold, because there is simply so much empty room before you finally reach the warm band. This means the inner system becomes a vast, bright but frozen gulf with no solid, temperate surface anywhere near the star. However, there is a brutal catch. While luminosity rises dramatically with mass, stellar lifetimes shrink. A 10 solar mass star may only remain on the main sequence for around 20 million years before swelling, changing, and ultimately dying, compared to the sun's 10 billion years. It should be noted that complex life on Earth needed several billion years of relatively stable conditions. Our hypothetical giant star Earth would have to rush through chemistry, biology, and evolution at speeds nature has never shown us, and that is only the clock. The quality of the light also changes. Massive stars pour out far more ultraviolet radiation, flare more violently, and can strip atmospheres with intense particle winds. So even if a distant orbit gives you the right total energy, the spectrum and variability can damage DNA, erode an atmosphere, and sterilize surfaces. Star factors and planet factors start to pull in opposite directions. Optimistically speaking, you might still ask, could a distant, shielded, Earth-like world somehow beat the odds? So it's time to find out the truth in the next next step of the puzzle. Even before biology, can such a planet actually form, grow to Earth size, and keep its atmosphere, while the giant star's very short timer is already counting down? Inside the blast furnace, disks, snow lines, and planet building around giants. So, let's begin with the very first obstacle, the nursery itself. If you drop a massive, blue-white giant into the center of a young disk, you do not get a peaceful version of our early solar system. You get a blast furnace. The inner regions of the disk are so hot that dust grains can literally vaporize, while intense ultraviolet and X-ray radiation blaze out in all directions. Evaluating this kind of system for planet building is tricky. Around our sun, the protoplanetary disk was relatively cool and long-lived, a gentle fog of gas and dust that had a few million to 10 million years to settle into planets. But while a sun-like star glows steadily, a 10 solar mass giant shines thousands of times brighter. This means the top layers of its disk are constantly being stripped away by powerful stellar winds and high-energy photons, like sandblasting on a cosmic scale. In the hunt for alien life, one key concept is the snow line, the distance from the star where water and other volatiles can freeze into solid ice. Ice is crucial because it lets tiny grains stick together efficiently and rapidly build big planetary cores. Around our sun, that line sat a few astronomical units out, near the orbits of the giant planets. Around a luminous blue star, the snow line is pushed tens of AU away, perhaps out near where the Kuiper belt is in our own system. It should be noted that this shift does two things at once. Close in, the disk is so hot that even many rocky minerals struggle to survive, reducing the raw material for an Earth-like planet. Far out beyond the snow line, there is plenty of icy material, but the orbital periods are long and the disk is being eroded from above. So can planets really assemble before the gas is gone? Here is where JEST, ALMA, and other observatories give us harsh news. When we look at massive stars in young clusters, we see their disks vanish quickly. Photoevaporation driven by ultraviolet radiation can clear the gas in under 1 to 3 million years. That is dramatically shorter than around sun-like stars, and it squeezes the entire timeline for core accretion. Planetary embryos must coagulate fast, or not at all. Paradoxically, giant planets might actually have the advantage here. Out beyond the distant snow line, icy solids can pile up quickly, forming massive cores that gulp gas while it is still available. An Earth mass world at 20 to 40 AU can, in principle, grow too. But it is racing the clock, and it risks being overshadowed by rapidly forming gas giants that steal material and stir the disk. Optimistically speaking, let us imagine one rocky planet does make it, roughly Earth mass, orbiting far from the glare yet still inside the shifting Goldilocks zone. So it's time to find out the truth. Under that relentless ultraviolet onslaught and those fierce winds, can such a fragile world keep an atmosphere, hold on to its oceans, and stay habitable for more than a cosmic heartbeat? Or will the very furnace that forged it also strip it bare in the next act? Life under a harsh sun, radiation, atmospheres, and surface conditions. So, what would it actually feel like to stand on that world, under a giant star that could tear your sky apart? We talk about habitability in terms of distance and temperature, but for anyone on the surface, the first thing you would notice is the light. Look up, and the sun is a blue-white disk, still large and painfully bright even from tens of astronomical units away. Shadows are razor-sharp, like you are living under a permanent welding lamp. The landscape is washed in a harsh, icy glare, and the sky above is flooded with ultraviolet. Our own yellow star would seem, by comparison, almost gentle. It should be noted that this is not just about brightness, it is about energy in the most biologically dangerous part of the spectrum. O and B type stars pour out high-energy photons. This means that, even out in the Goldilocks zone, the top of the atmosphere is under constant assault. Molecules are split apart, electrons are knocked free, and any protective ozone layer is in a permanent state of crisis. Could an Earth-like planet ever build a stable shield the way we did? Or would ozone form for a while, only to be shredded again and again by each surge of ultraviolet and X-rays? Down where the air thins into space, the situation becomes even more extreme. Intense OV heats the upper atmosphere until it swells and escapes in a slow, continuous leak. Stellar winds from a massive star slam into it, dragging charged particles and lighter gases away. Hydrogen and helium go first, but over millions of years, even heavier molecules can be stripped. In the hunt for alien life, this is a brutal filter. An Earth-sized planet might lose much of its air long before complex organisms have time to evolve. Could a powerful magnetic field save the day? A strong dynamo could carve out a cavity in the stellar wind, forcing most of the charged particles to flow around the planet. But while the field deflects some radiation, it also traps particles in vast radiation belts. Auroras would be spectacular, possibly visible down to the equator, yet they would be a warning sign. Bursts of energetic particles could reach the ground, turning the surface into a place where unshielded life is constantly stressed, if not sterilized. By contrast, our calm yellow star sits in a kind of sweet spot. Its ultraviolet output is high enough to drive chemistry, but low enough that Earth's atmosphere can survive for billions of years. Around a giant star, the same fragile envelope of air might have to be endlessly replenished by volcanoes or comet impacts just to stay thick. Optimistically speaking, that could buy a brief window of habitability, but is a few million years really enough? So, let's begin to ask whether any biosphere there could ever escape its infancy before the light that nourishes it strips it bare. Racing the clock. Can life evolve in 20 million years? So if a few million years is all we get, we have to ask a brutal question. Is that remotely enough time for life to light up this world before the star burns out? We have set up a best-case scenario so far. Our Earth-sized planet orbits at a safe distance in the Goldilocks zone of a giant star, far enough that its surface is not instantly sterilized, close enough that water can stay liquid. It clings to an atmosphere under a hail of high-energy radiation. But there is a catch we cannot escape. A massive star might only stay on the main sequence for 10 to 20 million years. That is the entire window for habitability. Compare that to our own system. On Earth, the earliest solid evidence for simple microbial life appears more than 500 million years after the planet formed. Complex multicellular organisms take over 3 billion years. Technological intelligence, roughly 4.5 billion years from the beginning. This means our sun's slow, steady output gave biology an almost absurdly generous deadline. Around a giant star, that deadline shrinks by a factor of hundreds. In the hunt for alien life, that is a terrifying compression, but while the timescales look hopeless at first glance, we should at least ask whether the environment itself could speed things up. A giant star floods its planets with ultraviolet light and charged particles. Instead of a gentle yellow glow, the sky would be a relentless chemical engine. UVA can tear apart molecules in a young ocean, building complex organics in the process. In shallow seas and steamy atmospheres, reaction rates could be higher, mutation rates faster, entire genetic experiments running on fast forward. Optimistically speaking, perhaps the steps that took Earth hundreds of millions of years could be squeezed into a few million. But even if that works, what do we actually get? A stable biosphere, or just a brief microbial flicker? It should be noted that ecosystems need more than chemistry. They need time for feedback loops to settle, for niches to form, for evolution to explore. Around a giant star, the climate is not just short-lived, it is drifting as the star brightens. Oceans may boil at the edges, atmospheres may erode faster than life can adapt, so we are left with a sobering possibility. Maybe microbial mats appear, maybe simple plankton cloud the oceans, and then the light that created them slowly turns hostile. Is there any chance for forests, for animals, for technology in such a rushing timeline, or is complexity simply out of reach? So it's time to find out the truth. To answer that, we have to follow the star itself. How quickly its brightness changes, how violently it dies, and whether any fragile biosphere could possibly survive the final act. No certainties in a violent cosmos, data limits and open questions, but before we follow that star into its final act, we need to be honest about something. How much of this do we really know, and how much are we carefully, scientifically guessing? Massive stars are rare. While red dwarf stars fill the galaxy, the true giants are outnumbered, and usually far away, huddled in crowded, dusty stellar nurseries. This means our telescopes struggle to see the fine details. A small Earth-like planet deep in that glare, almost invisible. Even the disks of gas and dust around these stars are hard to measure precisely because the very light we need is scattered and absorbed before it reaches us. So when we talk about a protoplanetary disk around a blue giant, we are often working with fragments. ALMA can map clumps of dust tens of astronomical units out. DWEST can pick up warm gas close to the star, but the tiny rocky building blocks that might become an Earth analog, those are still below our direct detection threshold. It should be noted that our models are only as good as the assumptions we feed them. How fast does the disk evaporate under a flood of ultraviolet radiation? How strong are the stellar winds that strip away gas? How tangled are the magnetic fields threading the disk? Change any of these, and the timeline for building planets shifts dramatically. In the hunt for alien life, that timeline is everything. Simulations that track disk dispersal or atmospheric escape often have to pick a starting disk mass, a wind strength, a magnetic geometry, and then run with it. Optimistically speaking, we bracket the possibilities with many runs. But while this gives us trends and probabilities, it does not give us a single, guaranteed outcome for every system. Here's the pattern interrupt. Right now, even with JWS and ALMA, we mostly see massive stars with very young disks, or with their disks already gone. We do not yet have a clear, confirmed case of a mature, quiet, Earth-like planet peacefully orbiting a 10 solar mass star in the Goldilocks zone. This means that when we imagine such a world, we are extrapolating, taking baby pictures of planetary systems and trying to predict their adult lives. So when we say that an Earth around a giant star is unlikely, or that any habitable window would be short-lived, we are talking about odds and physics, not absolute bans on life. Given enough stars, enough time, and enough strange chemistry, the universe can surprise us. At the same time, some boundaries are very hard to break. Stellar lifetimes, luminosity, radiation output, these obey well-tested physics. Within those constraints, we can still meaningfully ask what an Earth in such a system would face, and how fast its chances for life would open and then close. So, let's begin to apply those boundaries. If we actually placed an Earth-like planet in the shifting light of a giant star, where could it orbit? How bright would its skies be? And how long would that fragile habitability really last? A system on fast forward, mapping a giant star solar system to answer those questions. We first have to step back and look at the entire system. What does a solar system wrapped around a giant blue star actually look like if we press fast forward on cosmic time? Evaluating a star system for compatibility with life is tricky. Around a giant, almost everything we are used to is compressed inward, fried, or blown away. The inner few astronomical units are less a calm inner solar system and more a blast furnace. Any small rocky planet that formed close in would be stripped down to its core, its atmosphere and oceans boiled off by extreme ultraviolet light. This means the only survivors near the star are likely hot gas giants hugging tight orbits, or bare, airless rocks glowing red under relentless radiation. So where does an Earth-like world go? Far out. A 10 solar mass star can shine roughly 10,000 times brighter than the sun, pushing the Goldilocks zone tens of times farther away. Instead of Earth sitting at 1 AU, the habitable band might begin at 20 AU and stretch out toward 50 AU, deep into the region where, in our own system, we find Uranus, Neptune, and the Kuiper Belt. It should be noted that at those distances, a single year could last hundreds of Earth years, with planets crawling slowly around their brilliant, short-lived sun. That architecture is the mirror image of what we see around a red dwarf like TRAPPIST-1. There, multiple Earth-sized planets are crammed inside the orbit of Mercury, packed so tightly that their gravitational tugs are measurable in the data. But while TRAPPIST-1's family is compact and huddled close to a dim ember, our hypothetical blue giant system is stretched out and sparse, its potentially habitable worlds widely spaced, each one isolated on a huge, slow orbit. In the hunt for alien life, that wide habitable zone is both a challenge and an opportunity. Dynamically, there is room for several Earth-mass planets on stable paths between 20 and 50 AU, along with massive gas giants hosting icy moons. Optimistically speaking, you could imagine a chain of Europa-like moons with subsurface oceans, all circling distant giants, themselves basking in intense but thermally comfortable starlight. Picture it, 3 or 4 Earth-sized planets, each with thick atmospheres, oceans, and clouds, all lit by a blazing blue sun that turns daylight into something closer to an arc lamp. Between them, swollen ringed planets with glittering ice moons, each world a separate experiment in habitability, all coexisting in the same brief cosmic moment. But how brief is that moment, really? While a red dwarf's Goldilocks zone can remain stable for trillions of years, a massive blue star races through its life in only a few tens of millions. So it's time to find out the truth. In a system like this, does water have enough time to settle, chemistry to begin, and life to take hold at all? Or does the star's death arrive before the story can even properly start? Planet by planet, imagining giant star Earths and their fates. So, let's begin by actually walking through this alien Goldilocks zone, planet by planet. If you dropped 3 different Earths into orbits around a giant blue star, what would they really feel like, and how long would any of them stay habitable at all? First, the Inner Edge Earth analog. This planet hugs the hot side of the habitable band, racing around its star in just a few of our months. Surface gravity is a little higher than Earth's, so every step would feel heavier, but that extra pull does not save it. The atmosphere is under constant assault from ultraviolet light, far more intense than anything our sun delivers. Water in the upper air is split apart, hydrogen escapes, and the planet slowly bleeds its oceans into space. Clouds would pile into a thick, steamy shroud, storms would rage, and then, as the star brightens, the whole climate tips into a runaway greenhouse. In the hunt for alien life, this looks less like a cradle and more like a short-lived steam bath. Move outward, and we reach the mid-zone Earth twin. Here, the planet really is Earth-like in size and mass, but the year stretches on for hundreds of our years because the habitable zone sits tens of astronomical units from the star. Days are bright, almost painfully so, but tidal forces are weaker than in many compact systems, so the planet can spin freely. It should be noted that early on, a thick atmosphere of nitrogen, carbon dioxide, and water vapor could build temperate oceans and continents, but as the giant star's luminosity climbs, high-energy radiation strips gases away and sterilizes the surface. Does life end there? Maybe not. Optimistically speaking, subsurface oceans, protected under kilometers of rock or ice, where deep-sea ecosystems around hydrothermal vents could outlast the loss of surface habitability by millions of years. At the cold outer edge, we place a super-Earth. This world is a little larger and more massive than Earth, with stronger surface gravity that helps it cling to a dense atmosphere despite fierce stellar winds. The sky might be thick and hazy, colored by complex molecules formed under relentless ultraviolet light. Days would be long and dim, the star a brilliant blue point rather than a wide yellow disk, casting hard shadows over frozen seas and patchy, thawed regions. As the star evolves, even this marginally habitable climate is driven first toward brief temperate conditions, then into global glaciation as the habitable zone races outward faster than the planet can follow. This means that, no matter where we place our three worlds, a pattern emerges. Inner edge planets steam away, mid-zone twins lose their air, outer giants freeze. All of them live on borrowed time, squeezed into a window of only a few million years, while our own sun offers billions. So it's time to find out the truth around a giant star. Can any biosphere grow fast enough to outrun the clock? The final act, supernova, aftermath, and what it means for us. So, what happens when the clock finally runs out? Our giant star does not drift gently into old age. After only a few million years on the main sequence, it begins to swell. Hydrogen in the core is exhausted, fusion shells ignite in layers, and the whole star puffs up into a bloated, blinding monster. The Goldilocks zone surges outward. Planets that once orbited in a comfortable band suddenly find themselves under a floodlight. Climates snap. Oceans boil or freeze as the star brightens by factors of tens, then hundreds. Seasons, if they ever existed, are replaced by chaos. Even before the final explosion, ultraviolet radiation strips atmospheres, tears apart molecules, and turns any remaining surface water into steam and plasma. In the hunt for alien life, this is the phase where even the most resilient biosphere is pushed to the brink. Then, the core collapses. In a fraction of a second, gravity wins, the inner regions implode, and a shockwave races outward. The star detonates as a supernova, briefly outshining its entire galaxy. From any surviving planet, the sky would not simply brighten. It would become a wall of light, a flash so intense it could cast sharp shadows on worlds light years away. This means gamma rays, X-rays, and high-energy particles slam into nearby planets, shredding atmospheres and sterilizing any exposed surface. Rocky worlds close in are blasted, their crusts shaken by seismic waves triggered by the changing gravitational field and the impact of ejecta. Even distant outer planets are swept by the supernova's shock front, their upper layers chemically rewritten. It should be noted that, in this environment, habitable is reduced to tiny refuges, not Earth-like paradises. Could anything survive? Perhaps, deep beneath the surface of a planet, microbes sheltered kilometers down might ride out the radiation storm, feeding off residual heat and chemistry. On icy outer moons, thick ice shells could act as armor, keeping subsurface oceans intact. Rogue planets, ejected earlier from the system, might drift safely between the stars, their internal heat and buried oceans untouched by the blast. Ironically, the destruction also sows the seeds for future worlds. The supernova flings heavy elements, carbon, oxygen, iron, even radioactive isotopes, back into the interstellar medium. Later generations of stars and planets, including systems more like ours, are built from this enriched debris. Optimistically speaking, every calm yellow star may owe its complex chemistry to a long-dead giant, and we can actually watch the prelude to this cycle. JWST and other telescopes see massive blue and white stars in crowded clusters, their radiation already carving away the gas and dust disks around neighboring, smaller stars. Planet-forming material is being eroded in real time, which means the the fates of future planetary systems, including any that resemble our own, are being edited by these short-lived titans. So where does that leave the Sun? Compared to a giant, it is modest, almost quiet. But while our star will never blaze as bright as a supernova, it offers something far rarer: time. Roughly 10 billion years of relatively stable light, a Goldilocks zone that drifts slowly, and flares that so far have not erased our atmosphere. For slow, complex evolution and technological civilizations, a middleweight star like the Sun may be near optimal. But if that is true, and giant stars are so hostile to long-term life, how does that reshape our odds in the wider universe? And what kinds of worlds should we really be searching for next? So, could we ever live there? Final verdict and viewer challenge: this means our picture of the cosmos shifts in a subtle but important way. If giant stars really do slam their habitable windows shut almost as soon as they open, then most of the universe's bright, dramatic light shows are probably dead ends for long-term life. We have traveled from scaling up our own sun, to stretching the Goldilocks zone tens of astronomical units outward, to watching protoplanetary disks get stripped by ultraviolet light and stellar winds. We mapped how an Earth-like planet might orbit there, how its atmosphere would be battered, and how a fragile biosphere would race the clock of a star that lives only 10 or 20 million years. In the hunt for alien life, giant stars offer wide, theatrical stages, but on brutally short and hostile terms. So it's time to find out the truth. Could an Earth-like world actually exist around a giant star? Optimistically speaking, yes, for a moment. The data and physics suggests that rocky planets can form, liquid water can briefly pool, and for a few million years, conditions might look surprisingly habitable. But while that makes for a spectacular setting, the combination of rapid disk dispersal, intense radiation, and a life expectancy shorter than the time it took complex life to even get started on Earth makes anything like our own biosphere extremely unlikely. It should be noted that this is the deeper insight hiding underneath the fireworks. Our calm middleweight sun is not just convenient, it may be near the lower bound for stars that can host stable, life-bearing planets for billions of years. Red dwarf stars live far longer, but bring flares and tidal locking. Giant stars bring light, but almost no time. A star like the Sun sits in a narrow band where the Goldilocks zone is steady, atmospheres can survive, and evolution can take the slow road. That might make our entire system rarer than it first appears. But imagine, just for a moment, that a civilization did arise around a blue-white giant. What would that feel like? Children learning that their star is already middle-aged. Scientists measuring its changing spectrum across a single lifetime. A culture forced to become early spacefarers, designing arcs to leap outward to a quieter red dwarf or a yellow sun long before their own star explodes. Their whole history would be a countdown. Ours, by comparison, is a leisurely afternoon. So, let's begin a different kind of thought experiment. If you could design a universe, which type of star would you choose to orbit? A giant, for drama? A sun-like star, for balance? Or a tiny red dwarf with trillions of years to play with? Tell us in the comments, and tell us what kind of planet and atmosphere you would build there. If you enjoyed this deep dive into extreme habitability, subscribe for more cosmic what-ifs, and do not stop here. Our next episode explores the opposite extreme: life around tiny, ultra-long-lived red dwarfs. Click through, and let us see what happens when the universe gives life almost too much time.